There's a special vector called the zero vector that has the property that all of its coordinates are equal to 0. Now you can have a separate zero vector for every single dimension of Euclidean space. So for example, let me write down a couple here. So the two-dimensional zero vector, I'll give it the symbol 0 as a label. It's got two coordinates that are both equal to 0, and that belongs to R2. Now there's another zero vector that belongs to R3 that has three coordinates that are all equal to 0. And I could do the same thing for R4 and R5 and R6. We use the same symbol to denote the zero vector in every case. And with the context, whatever context it appears in, that's what you have to rely on to make it clear which dimension you're working on. But you always have access to that vector no matter what. If you're dealing with R2, well, then you've got the two-dimensional zero vector. If you're dealing in R3, then you've got the three-dimensional zero vector. Now, just like we did in the previous pages, if you're dealing with R2 and R3, then you can take any vector and you can identify it with a point, or you can identify it with a position vector and actually draw an arrow that goes from the origin to that point, just like we've done in the pages leading up to this. But if you tried to do that with the zero vector, you'd end up with the origin as the point that you identify that vector with. And if you try to draw an arrow, well, there'd be nothing there. Because an arrow that goes from the origin to itself, well, there's no length to that arrow, so you'd essentially have an invisible arrow. The other comment I want to make is, and I've actually been taking advantage of this in the preceding example without comment, but I want to address it now. If you have any vector, and this doesn't just apply to 2 or 3 dimensions, this applies to any dimensions and higher dimensions as well. If you see this notation, you just see a negative sign in front of the vector. Technically speaking, we haven't actually said what that means, but it's the same thing. You interpret it the same way that you interpret a negative in front of an ordinary real number. The easiest way to think about it is just think of it as -1 multiplied by that number. So it has the same effect as multiplying the vector by the scalar -1. So it's just the same. It's the vector that has the same length, but it's in the exact opposite direction. Okay, and so what comes next to finish this page off is a list of properties that apply to all vectors, no matter what dimension you're living in. So let's start with just laying out the fundamentals here. So let's say we've got 3 vectors, and you can see they're all in Rn, but I haven't told you what n is. The idea is that n is general. So we could have 3 vectors u, v, and w. Maybe they're in R2 if n is equal to 2, or maybe they're in R3 if n is equal to 3. But the point is, the important part is that they're all in the same dimensional space, right? So they're either all 4-dimensional vectors, or they're all 5-dimensional vectors, or they're all 6-dimensional vectors. There's no mixing, right? You won't have u be 3-dimensional and v and w be 5-dimensional, say, for example. That wouldn't make sense. So from this point on, for the rest of the items in this list, just assume you've got 3 vectors u, v, and w that all have the same number of coordinates, and then you've also got 2 scalars, so 2 real numbers, c and d. Okay, so the first property just says that if you add up the vectors, it doesn't matter what order you do it in. Okay, that's referred to as the commutative property of vector addition. The third property says if you decide to add up 3 vectors, it doesn't matter which ones you add up first. Remember, if addition is what's called a binary operation. It's something that takes 2 arguments, that, in other words, the things that you want to add together, which is there's got to be 2 of them, and then what it gives you back as a result is it gives you back the sum of those 2 input values. So in the case of addition here, if you want to add up 3 things, well, technically speaking, that doesn't make sense. You have to pick 2 to add up first, and then you can add the third one to the result. So for example, on the left-hand side, if you read this carefully, left-hand side of this equation, you've got 3 vectors u, v, and w. So what you want to do here is you're going to add up u and v first, then whatever the result is, you add that to w. So that's both times you're only adding up 2 vectors at a time. But on the right-hand side, you're doing something conceptually different. First, you're adding up the vectors v and w, and then whatever the result is, then you add u to that result. Now, the fact that you see these 2 expressions on either side of an equation means the property here is claiming that these 2 things are equal, no matter what the vectors u, v, and w are. So that's referred to as the associative property of addition. So that's the nice feature of addition. And because of this property, sometimes you will see 3 vectors added up. In fact, I shouldn't even say sometimes, you'll often see 3 vectors added up without brackets assigned to any particular 2. Because of this property, there's no ambiguity in doing that. Okay, so the third property here says, and this is probably not a surprise, but if you take any vector and you add to it the 0 vector, there's no change, right? So if I start with a vector u and I add the 0 vector, the result is just going to be whatever vector u I started with. The fourth property says if you take any vector, call it u again, you always can write down negative u. Remember, negative u is defined in this way. It's just -1 multiplied by the vector u. So if you take negative u in this fashion and then you add it to u, this property just says you're always going to get the 0 vector. So this is referred to as the additive inverse property, and property 3 is referred to as the additive identity property, or specifically, the 0 vector is the additive identity of Rn, and negative u is the additive inverse of u. Okay, and properties 5 and 6 are both referred to as distributive properties, although they're slightly different. Property 5 says, well, let's think about it. If you've got 2 vectors and you want to add them together, and in fact, let me just change it so it's only focused on the left-hand side for the moment. If you've got 2 vectors, u and v, and you want to add them together, you know in advance that the result is going to be another vector. And you're allowed to multiply any vector by a scalar. So let's multiply the resulting sum by the scalar c. Well, this property is telling you there is another way to evaluate that. You could take just the vector u and multiply it by the scalar c, then take the vector v and multiply it by the scalar c. And then when you do that, you're going to get a separate vector for each of those calculations. You can then add them up. That's what the right-hand side is really saying to do. And this property is promising you that you're going to get the same thing, whichever method you choose. So you can either add the vectors up, then multiply the result by the scalar. So you're only doing one scalar multiplication. Or on the right-hand side, you could perform 2 separate scalar multiplications and then add up the results. So property 5 says either of those are okay. You'll always get the same thing. Property 6 is similar, but in this case, the addition is taking place among scalars. So on the left-hand side of this equation, you've got 2 scalars, c and d, and you're adding them up right off the bat. So that addition between c and d, that's not vector addition, that's scalar addition. That's the addition that you grew up all through elementary school and high school learning about, right, and using. So that's the addition you're very familiar with before this course. But then once you add those 2 numbers together, c and d, the result of that addition is now a scalar that is being multiplied onto the vector u. So that's what's happening on the left-hand side of the equation. On the right-hand side, there's 2, again, not just like, but similar to the previous property, there's 2 scalar multiplications happening on the right-hand side of this equation. In both cases, the vector is u, but in one case, the scalar is c, and in the other case, the scalar is d. So there's 2 scalar products that are computed, and then the result is added up. So property 6 is telling you that you can do that in either way, and you'll get the same result. Okay, property 7, this one is neat. It almost looks a little bit like it almost looks like property 2, but for multiplication. But be careful, it's not quite the same thing as saying that, because in property 7, in both cases, you've got both sides of the equation have 2 products. But on the right-hand side, there's 2 scalar products. Let's start with the right-hand side this time. First thing you have is a vector u, and it's multiplied by the scalar d. Now the result of that product is going to be another vector, right? If you take a vector and multiply it by a scalar, you're going to get another vector. Now that vector that you get is then going to be multiplied by the scalar c. Okay, so that's what's happening here. So in the end, you're going to have a vector that has been multiplied by a scalar twice. You're starting with u, you multiply it by d, whatever the result is, then multiply that by c. On the right-hand side, or probably on the left-hand side, there's only one scalar multiplication happening. The multiplication inside the brackets, that's just multiplication of 2 real numbers, c and d. That has nothing to do with vectors. But once those 2 numbers, c and d, are multiplied, then the result is now a scalar that's going to be multiplied onto the vector u. And in keeping with the theme of all these properties, property 7 is just telling you that you can do those in either way. You can take either of those approaches, and you are guaranteed to get the same result. Okay, property 8 isn't really surprising to most people if you've given some thought to this. This follows directly from the definition of multiplication. But if you have a vector, let's start with the first equation here. If you have a vector u, and you multiply it by the scalar 1, right? 1 is a real number, so that counts as a scalar. If you multiply it by 1, you're just going to get the same thing. You're not going to make any change. Remember how scalar multiplication is defined, right? You just multiply each coordinate by the scalar. So if you multiply every coordinate of u by 1, you're not going to change any of them, and the coordinates are going to be the same. But if you multiply the vector u by the scalar 0, well, then you're going to get the 0 vector. Because if you multiply each coordinate of u by 0, the result of each of those multiplications is going to be 0, since 0 times any other real number just gives you 0. So in the end, what you get is a vector, all of which the coordinates are equal to 0. So you end up getting the 0 vector as an answer. Notice that this 0 is bolded because that's not the real number 0. That's the 0 vector, like you see over here. These are just examples, right? But in general, depending on what your value of n is, depending on the dimension of Euclidean space that you're working in, that'll determine what dimension this vector is. But the 0 that you see on the left-hand side of the equation, that's just the ordinary real number 0 that's being multiplied onto u as a scalar. Okay, and then the last property is if you have the 0 vector and you multiply it by any scalar, so I use the letter d here to represent the scalar, the result is just going to be the 0 vector, right? And again, think about how scalar multiplication works. This shouldn't be a surprise. If you have a 0 vector, that means all the coordinates are equal to 0. Well, multiply all those coordinates by d, and you're just going to have d multiplied by 0 a whole bunch of times, and the result's going to be 0 every time. So all the coordinates of the product are going to be 0. So that's why the product actually gives you the 0 vector.